Hi everyone, and thank you for coming to my presentation, for viewing it. My name is Romit Maulik, and I'm a postdoc here at the Leadership Computing Facility at Argonne National Laboratory. And in what follows, you will be viewing a pre-recorded version of my pre-recorded talk, because I gave this talk just a few days ago at a seminar here in Argonne. So I hope you enjoy the talk, and please feel free to reach out to me for further information. And I hope to see you on the 24th of September, if I'm not wrong, for the live session where we can have a chat. Thanks. All right, so let's see. Okay, so this is kind of the outline of what I'll hopefully try to cover today, right? So we have three major sort of verticals that I'll be talking about. The first one is doing some, so it's all of this is going to involve a lot of surrogate modeling, because that's basically the type of work that I do. In the first section, I'll be talking about surrogate modeling for shape optimization, and that's definitely very aligned to the abstract you must have read. The second portion of my talk will be looking at surrogate model discovery, or search, for geophysical emulation. So it's a slightly different type of system optimization, which we want to optimize for in the sense of finding a very good surrogate model. And finally, in the last portion of today's talk, I'll be sort of doing some self-advertising. I hope you forgive me for that ahead of time, where I'll be talking about some code that we've been writing here in LCF to enable a lot of the methodological work that's happening around us. And I hope that piques your curiosity. Okay, so let me start with part one. This is related to aerodynamic optimization. So this is work done with MCS's very own Ashwin Raghunathan, looking really happy over here, probably because of the quality of work that we've been doing recently. And what we want to do in this particular work is come up with a framework that helps us find the optimal shape of a transonic airfoil, but not have to go through the painstaking process of actually doing a CFD or a PD-based system solve every time we want to evaluate a configuration, right? And there have been other groups around the world who have used different forms of surrogate modeling to actually accomplish this, right? So we'll be looking at a very simple surrogate model because we'll be trying to tackle a very different problem. I'll get to that in a while. But there are many different ways to build your surrogate models, and I have dabbled in all of these. For example, you could have something called a projection-based surrogate model, where you still solve a system of equations, but you change the basis in such a way that it's now much cheaper, right? You can also use, for example, a neural network to directly predict how, say, for example, a particular configuration performs. We'll be doing that. You can even, for example, try to use neural networks to directly predict your quantity of interest. So, for example, for an airfoil, this could be the drag or the lift coefficients, and you can directly go ahead and predict that rather than worrying about how the flow looks like, right? Okay, so just to highlight, that's what we'll be doing over here, right? This is our problem statement. Very briefly, it's basically an airfoil. It's the RAE2822 airfoil, which is parameterized by 8 control parameters, which are supposed to be within this hyperrectangle. And although this is not very visible to the naked eye, changing these parameters leads to slight variations in the shape, and this actually controls the location of a shock that forms on top of the airfoil. I'll give you some examples soon, right? And depending on your configuration, and this is hard to say, but you can kind of put an upper bound on how long it takes to solve for one configuration of this airfoil, and we can keep that from between 10 minutes to an hour. And what we want to do is we do not want to have a lot of these 1 hour solves to evaluate a particular configuration of the airfoil, right? A second important point to note is that, and this is something that I'll be highlighting throughout this talk, is that I like to make the assumption going forward whenever I build a surrogate model, that my data is coming from something that is completely black box. So for example, over here, let's say you run a commercial solver, right, like star CCM or ANSYS, and you don't have access to the numerics under the hood. You might know what they are, but you don't have access to the numerics under the hood. So there's a lot of surrogate-based models that are meant to run on the numerical solver, like, because they need access to the discretization, they need access to the numerical scheme information, and I'm going to assume that we don't have access to those, right? So that's another restricting sort of limitation. Okay, so. And these are the compressible steady-state Euler equations, so very standard sort of setup. Okay. Now, if you were to do a classical shape optimization of this particular problem, you'd want to do something like an adjoint-based optimization. So an adjoint-based optimization I mean, there's been a lot of work done in that, right? And the idea is basically to set up a cost function first, right? Which is J. I think I mentioned it. I haven't mentioned it yet. But J, for example, could be minimizing the drag for a certain set of parameters, or could be minimizing the drag while constraining to a certain lift, right? And you want to basically find the gradient of this objective function with respect to the control parameter so that you can search using that gradient information to some sort of solution, right? And but the problem with this is, just from a high-level perspective, that is extremely expensive, right? And because every time you sample a new configuration, you have to do a full-order solve to actually find what the value of the objective function is. In addition, you also have to solve to get the adjoint itself. So you actually have to solve to get the lambda, which is used for computing the gradient. So essentially, it boils down to having approximately 2 system solves for each sample configuration, and so it really puts a big strain on your computational budget if you're not careful. Right? We want to avoid this. Okay. So now what we go ahead and prescribe for this particular problem is the use of differentiable surrogates, for example. All right. So instead of going ahead and solving the PD system, can we emulate the PD system? In particular, can we directly emulate the lift and the drag, which were the objective function statements, which were in the objective function statements over here, so that our J is now a surrogate objective function, which is a function of my black box surrogate model, right? So the W and B over here, for example, in our case, are the weights and biases of a neural network, right? So we've basically used some examples from the PD solver and fit a surrogate model for that. And now we'll use this surrogate model to basically replace wherever we needed the PD solve. So fortunately, a neural network calculating the gradient of the objective function or the gradient of the output with respect to the input is very trivial. It just uses backpropagation, and in TensorFlow 2, this is just one line of code. So to actually fit a neural network, compute this gradient, and put it back into, say, a gradient-based optimizer that you might get from SciPy is extremely trivial, right? And in Python, it's very, very simple. And in the process, what you've done is you've got rid of the forward problem, and you don't have to solve the adjoint system as well. So this is what sort of motivated us to do this particular work, right? But we ran into problems. We'll show you in a while, okay? So in terms of the surrogate model itself, I'm not in the business of making these incredibly complicated deep learning frameworks because often I like it if the physics itself can do the heavy lifting for us, right? So in this particular case, our surrogate model is extremely trivial because this is a proof of concept work. But it goes ahead as a fully connected network. You could whip this up in less than 5 minutes. And then I train it on my drag and lift coefficients. You can see it gets the trend right, but there's a little bit of deviation, and that is going to be what motivates the second part of this particular talk, right? Okay, so how does it work? Well, these don't look so good they look kind of similar to the naked eye, but you'll see some contours which make this clear. But what we observe is not surprising. If we use only 30 training samples, so 30 PD solves, to train, where each data point is basically the control parameter and the corresponding lift and drag. We can do a optimization using the surrogate model, and you can say somewhat get close to the truth. The truth is obtained from a 2000 DOE experiment. So we basically sampled this 8-dimensional space 2000 times. Now, just to let you know, in a practical case, we wouldn't know what the truth is, right? So that's something that you need to keep in the back of your mind. It's all very nice to show results on test data, but in practice, you don't have test data, right? But what we see over here is not surprising. As we increase the number of training data points in our DNN, our performance gets better. And I'm not showing more, but when we go up to 100, 200, which is not something we want to use for training because we want to keep it data efficient, we end up getting even closer to the truth. The adjoint, you can see, is also competitive. It's a little off in the front, but it captures the trailing edge nicely. And the adjoint required 50 iterations, so that means it required 100 system solves approximately to get to this particular configuration, whereas we did not require any system solves, but we did require 30 to train the framework, right? So yeah, two observations: more training data, better performance of the surrogate adjoint, and changing the objective function. For example, the adjoint, every time you change the objective function, you have to go ahead and resolve the system another 50 times, for example, if that's your budget. But in our case, you don't have to. Your method is already trained, right? So we were happy at this point of time, right? And this is kind of like a visual confirmation of the same. So if you have a baseline, by baseline, I mean it's the center of the hyperrectangle, a naive selection of parameters. You see the location of the shock. And when you optimize, for example, in the true case, the shock moves towards the front of the airfoil. And that is what the DNN is also able to mimic to a certain extent, right? So this is good so far. We were excited. A more quantitative comparison of the same thing. So, for example, the baseline does not get what these are the pressure contours on top of the airfoil. So it's basically taking this quantity that you see over here on top of the airfoil and just scanning it. And you can see that the adjoint gets close to the right contour, and the DNN, it's not quite there yet, but it's definitely trying to get the profile right, okay? So we were happy at this point of time, and we thought, oh, well, we can change the objective function and we can do much better. So we went ahead and did a lift constraint drag optimization. So we constrained the lift to 1, and we wanted to see if we could get close to the best possible profile. And this surprised us. We weren't getting as good a result, and it's because we used only 30 training points in our deep neural network, and not a collaborator. This is just a very popular meme out there, the Harold hide the pain meme, basically. So, and this is asked to me at almost every talk I give about surrogate modeling, and then people say, okay, what if you start, wanting to make predictions outside your training domain, and especially in an optimization framework, you don't have any control. It could very well go ahead and start making some really poor predictions, right? And so this is what kind of gave us pause, and we decided to go ahead and try something novel to fix this problem, where your extrapolation is a problem and you are in a data limited regime for at least for the training, okay? And what we went ahead and used to solve this problem is basically hybridize some elements of traditional black box function optimization. For example, generic Bayesian optimization. I'm sure a lot of the members of the audience are familiar with this. So the idea over here is that during your online phase, right, instead of doing a gradient-based optimization, you go ahead and you sample, given a certain budget, which is Q over here, you sample some new points to do some exploration of your response surface, and then you go ahead and keep updating, for example, a surrogate model that was predicting your target quantity of interest. And hopefully at the end of this iterative process, and there are some details over here that you can look at, you can go ahead and find some nice locations. The neat thing about Bayesian optimization is that there is no extrapolation as such, because every time you sample a new point, you will actually sample from the true PD system. So you will go ahead and solve the true PD system, right? And we want to leverage that, but we want to ensure that the total budget for the Bayesian optimization is much lesser than the 50 iterations we were using for the adjoint, right? We want to keep Q low. But so what we are saying essentially is we don't want to give away online, we don't want to remove online cost altogether because extrapolation becomes a problem. We want to keep some online cost, but we want to reduce it significantly from what the adjoint uses, right? Okay. So the approach we used to do this was that we actually built another surrogate model, and the surrogate model was a surrogate for the bias in the original surrogate model. So a lot to unpack over here. So you remember we had a DNN. Okay, we had a DNN that was predicting our lift and drag given the shape of the airfoil. And we saw that it wasn't perfect. It was getting the trend right, but it was missing out on that last mile of accuracy. To fix that, we went ahead and fit another a Gaussian process, actually. And a Gaussian process is a probabilistic model, right, to actually predict what the bias is, given the, for example, the shape of the airfoil. And it would use, so essentially it would use the DNN as a prior, right? So you would take the DNN prediction, get the Gaussian prediction for the bias, add those two, and you'd get your final prediction. Now, this gave us quite a little bit of flexibility because now it let us use, it converted a deterministic framework to a probabilistic framework, essentially. And with that probabilistic framework, we could go ahead and plug it into the Bayesian optimization. We call this the DNN-enhanced Bayesian optimization, right? So we have a DNN with a certain number of training points that's already trained. And then we use the same training points to fit a bias model, right? And that bias model is probabilistic, so the combination is probabilistic. And then we put that into a Bayesian optimization process. And then we restrict our budget to 10 only, which is a tenth of the adjoint-based optimization. And basically, we do a standard Bayesian optimization. And when we do that, lo and behold, we're able to actually improve quite a bit on the DNN-optimized problem, or the solely DNN-optimized solution, where you can see that because we have the luxury of 10 online iterations, we are able to handle this issue of making inaccurate, forecasts due to, or inaccurate predictions due to improperly trained deep learning frameworks, which are obviously very training data hungry, right? So it's kind of a hybrid in the sense of we are using, it's adaptive, right? So we keep updating the bias model as we make new predictions. So this is, you can also consider this to be like an actively learning type of framework. So yes, so just 10 additional online observations and not 100, and we are able to get quite close to the true profile, right? And so that was, for example, an example. Which example was this? So we went back and actually redid this for the drag minimization as well. So you can see it improved the drag minimization. But on the problem that we are having most trouble with, which was the lift constraint drag minimization. So this legend is wrong. This should be 30 over here, okay, on both. So for the lift constraint drag minimization problem, you can see where the DNN was quite far off. The addition of this online sort of correction type of method actually helped us get quite close to the truth. So we were quite happy with this. And so this work is under review right now. So I encourage you to check it out and get back to us if you have any questions. But you see what we've done over here. We've sort of we've let the DNN do its work, but we've also kind of given it some guardrails to ensure that it goes ahead and doesn't start predicting garbage, which is always a danger. All right, so if you want to summarize this first particular part of my talk, right? So if you do not want online costs at all, then you got to, it's cost amortization, right? That's what it boils down to. You got to generate more training data for the DNN, and then you fit a better surrogate model up front. However, be prepared for surprises if your surrogate starts extrapolating, right? I mean, you don't know if it's going to be extrapolating. You don't have the true data, right? This is a luxury that we were able to have by generating 2,000 DOE experiment training data set, or testing data set rather. So, but if you want to be a little more conservative, then you say that, okay, I will generate less training data, get a DNN which might get me almost all the way, but then I'll add some online cost to ensure that I don't extrapolate that I'm actually observing the system when I'm exploring for the optimal configuration, right, or for good configuration. So that was the first part of the talk, right? So I don't think our format allows me to answer any questions now, but I'll take any questions about this at the end. Okay. So the second part of the talk, we're going to make a little bit of an about turn and
Romit,
yes.
so sorry, I mean, there were a couple of questions on chat. I mean, if you want to, you can try to answer. It's all good. So one of them is from Ahmad. He asks whether you can use the training data build POD-based surrogate, and it is supposed to be optimal. So what are the advantages or disadvantages of ML-based surrogates compared to POD-like methods?
That's a good question. So we've actually done some POD-based surrogate modeling work. It really depends. So in terms of the POD-based surrogate, you have to reconstruct the entire, well, you don't have to reconstruct the entire field, but you do have to have the additional step of predicting the POD coefficients, then the POD coefficients reconstruct your field, and from the field you reconstruct your lift and drag coefficients. So it was just adding some bells and whistles. That wasn't really the sort of the motivation of the first part of the work. It was just to address this issue of extrapolation, right? But in principle, you could whip out the last few layers of the neural network and put in a training data which predicts the POD coefficients, and from that you could add some linear operations to reconstruct the field, to compute the drag, and then go back and do exactly the same thing, right? So sure, but we wanted to focus more on this sort of online improvement of the optimization, so we went simple, yeah. But in principle, they're equivalent. Okay.
Thanks. So there is one more question by Jared. So he asks, what is the reasoning behind your choice of Meton kernel?
There's no reason. We just went with what seemed most familiar to us. We've used this for a couple of other things. So I agree that there's a lot of art in choosing the kernel, but in aerodynamic optimization, there's been previous studies which have used that. So standing on the shoulders of giants, pretty much. Okay. So
one last question for this
sure.
section. Sorry about that. So you say. So the dimension is 8. This is by Misha. And he asked, why don't you just use a kernel method or GP, and why do you want to use DNN for such a low dimensional space?
Well, that was mainly the first part of the talk, which is it was ease of use, essentially. So you can easily calculate the gradient. I mean, I guess you could do that for a kernel method or for GP as well, but at least in TensorFlow, it's very easy to obtain the gradient of the objective function using the neural network. But also it kind of follows on from our previous work. So this is the continuation of our work that I referred to in the problem statement slide, where we did use a DNN for fitting a surrogate model. So that's how it's sort of built. In principle, yes, you could have like a surrogate model that's sufficiently black box, that's trained on low data so that it starts extrapolating, and then you can think of this method to correct that particular surrogate model as well. So the DNN is kind of just because everybody likes to use deep learning methods nowadays as black box emulators, so we figured we'd use that. Okay,
thanks.
So I'm going to move on now. Okay. Yeah. So the second part is something related to geophysical surrogate modeling search. I'm going to. So this is work with the DeepHyper team, in particular Prasanna, Roma, and Bethany, and of course Misha, who I think I answered a question for, is also actively involved in the development for DeepHyper. So DeepHyper is a framework that's available on Theta and Cooley, if not other systems as well. That actually helps you do hyperparameter optimization for neural networks or for actually any black box type functions. It also helps you do neural architecture search, and that's what this part of the talk will be about. So the neural architecture search will be for finding neural networks that are better surrogates, essentially. Okay. So just a very brief introduction into how DeepHyper works in terms of searching for neural networks, right? So if you are able to represent your neural network as a directed acyclic graph where the nodes are basically different operations that you can perform. For example, add a layer with a certain number of neurons, add dropout, add a skip connection, add an identity, do nothing, for example. And edges are paths along which, like, for example, an information will flow or a signal will flow through the neural network on its way from input to output. You could configure DeepHyper to actually select operations at these nodes, or even, for example, keep these nodes constant. And that lets DeepHyper at scale try out different configurations for neural networks, and then use, again, some sort of intelligent exploration of this really vast search space to come up with architectures which are good for your particular output or for your forecast task. So in this particular work, we actually looked at searching for LSTM architectures, right? And just very briefly, LSTMs are the specialized neural network architectures that are quite nice for handling data that are non-IID, so basically that are correlated in time. So you have, for example, time series data that's coming in from, any, in my case, geophysical process. And what we'd want to do is we'd want to do something simple over here. So we want to take an LSTM cell, which basically has an internal mechanism for preserving the effect of inputs in the past on current outputs, right? We want to take this cell and we want to see what combinations we can build using one LSTM cell. So just to clarify, we won't be changing the internal configuration of the LSTM cell, but we'll be taking a standard LSTM cell and seeing how in many different ways we can combine them together to come up with an off-nominal architecture, right? And why we want to use an LSTM? And this is how easy it is to set it up with DeepHyper. So within DeepHyper, all you need to do is write a simple Python function where you define what the input and output shape of your framework is. In our case, we have, for example, 8 time steps and a state vector of length 5. So the dynamical system we want to emulate has 5 degrees of freedom. And we want to say that there are 10 layers. The layers is an abstraction over here, but you can say that this controls the number of nodes that you have in your network. And at each node, you can decide to add operations, which could be, for example, an identity. It could be an LSTM cell with any of these particular. So you could have 16, 32, 64, etc. units. And you can add more possible choices over here. So this is a sort of like a function that tells you what you can have more activations. I've hidden out the activations here, but you can also choose among the spate of activations. It's fully compatible with the tf.keras API. So anything that you can write in a standard tf.keras setup, you can plug it into neural architecture search to search about. Okay, all right. So and if you have this, what DeepHyper basically does is it basically converts your neural network into an architecture into basically a list of floating point numbers, basically. Okay, so now if you randomly select these numbers, you can generate some really wacky architectures, and that's the cool thing. Now what we will do is we will look at that list of numbers. The length of the list remains constant because you've fixed the number of nodes, but we'll perturb that list to see how the architectures change and how their effects are objective function, are what that we want to minimize, which in this case is maybe some validation R squared, right? And so you can see over here I spent quite a bit of time coming up with these crazy architectures, which I'm sure no human could come up with on their own. So a really expressive way to search for architectures. Okay, and so we have a bunch of different algorithms for actually searching this really vast search space. We'll be looking at 2 today, but it's really just one that massively outperforms the other. The first one is reinforcement learning. Reinforcement learning, very high level. We have an agent that is also a neural network, ironically, that goes ahead and looks at the state. In this case, the state is given by, for example, the list of numbers, for example. So you can look at the list of numbers, and it looks at the list of numbers and takes an action. The action could be a perturbation that's applied on this list of numbers, right, within, again, a certain range. And given that perturbation, it gets a reward. And the reward is basically when we take this perturbed state and train it, we get a validation R-squared that comes out from this trained network. I'll remind you that this state is actually a neural network, right, that we get. And depending on the reward, it then goes back and iteratively this tries to explore the search space and come up with better architectures, right? And we use, I won't go into the details, but we use something called an actor-critic method where we have basically two neural networks. One actually goes ahead and predicts the next neural network to search for, and the other kind of critiques the niceness of that pick. And DeepHyper lets us actually deploy this at scale, so you have multiple nodes on Theta or Cooley that actually can evaluate networks in parallel. And then after certain intervals, you do some synchronization to update your agent, which is a neural network. Okay. Another, how much time do I have? Okay. So another method that we use that actually you will see ended up being far more superior is something that's derived from genetic algorithms, something that's been around for a while. So what we do over here is we generate a population of these neural networks. I'll remind you again, these neural networks are basically just lists of floating point numbers, or you can even frame it to be integers. And then we basically train all of these initially. We train all of these initially and we identify how fit they are. We basically do mutation, crossover, all that stuff to retain only the viable individuals. In this case, each individual is a neural network. So through evolutionary pressure, we go ahead and find better neural networks. And so that's kind of how we deploy this framework, right? So before going into results, let me just link this to geophysical flows. I promised to do that. So over here, what we want to do is we want to come up with LSTM architectures, correct? But what we want the LSTM to predict is, like Ahmed just noted, we want to predict the coefficients of a projection-based compression of our geophysical field. So let's say we take snapshots of data, right? And these snapshots, in our case, will be of these of the sea surface temperature. I'll explain the data set in the next slide. And the sea surface temperature will, you can stack them up into a snapshot matrix, use your algorithm of preference. We use the method of snapshots, but you can use an SVD as well to compute these optimal bases, using the POD. And then the coefficients of these bases, you can actually plot their evolution in time, right? And the LSTM will be used to search for the evolution of these coefficients in time and basically try to emulate the evolution of the sea surface temperature over a certain period, right? And this is the data set that I'm talking about. This data set is publicly available, and this comes in from NOAA. That's constructed by remote sensing observations from satellites and ship-based observations and interpolated onto a 1-degree grid. So it's not a very, well, it's available on a 1/4-degree grid, but that made this a little bulky, so we downsampled to 1 degree. And so that's basically a 360 by 180 grid on the surface of the Earth. And it's got some rich information. It has some seasonal dynamics, and it's also got some long-term patterns. So this box here tells us what we want to do. We want to perform a POD of this data set, collect the modal coefficient evolution in time, and we want to emulate this using the LSTM that DeepHyper finds for us. Okay. All right. So we go in and we compute. We try to search for this optimal architecture on 128 compute nodes of Theta. We limit ourselves to 3 hours of wall time. And these are some details, but basically during the search itself, we did not go ahead and do a full-blown training of the neural network. We trained only for around 20 epochs. And once we collected, for example, the best architecture, you could also collect a collection of the top few best architectures. We went ahead and then did a post-training. This was done on my laptop for maybe 5 times the epochs we used for the training. And then we set the number of layers to 5, right? And immediately you can see that as your wall time increases, the green line over here is the random search. So basically an unintelligent exploration of the search space. This guy keeps fluctuating about, 0.94, but the evolutionary algorithm very quickly, actually, even less than an hour, it goes ahead and finds a superior set of architectures. The reinforcement learning takes a little bit of time to get there because it has a strong exploration component compared to the evolutionary algorithm, which is a lot more exploitative. Okay, and you can see it comes up with this pretty wacky architecture. There's a bunch of skip connections and stuff. So now we want to go ahead and see how well this does on our task, on our emulation task. And just to make sure that this wasn't fortuitous, so we go ahead and we take the evolutionary algorithm and we just ran the same experiment 10 more times. And we saw that, yeah, it was performing in a similar manner. It was reaching a nice sort of performance within an hour. Okay, so since this was done at scale, we did some assessments on scaling. And in scaling as well, you can see as we increase the number of compute nodes on theta, the metric we use is number of unique architectures which are beyond this particular threshold. We are able to discover more and more architectures. This is using the genetic algorithm, so we call it aging evolution. So that's why it's AE. And when we compare this scaling with the reinforcement learning and the random search, you can see as we increase the number of compute nodes, the evolutionary algorithm is actually able to discover more unique architectures as we go forward. So this was a bit about the methodology. Now, something that you might be thinking about right now is it actually worth the cost, right? 3 hours of wall time on 128 compute nodes of theta is incredibly costly and also not very good for the environment. So we went ahead and actually compared this neural architecture search LSTM against some standard ML methods that you can whip up in less than half an hour. And we also went ahead, and this is obviously, there's no way to guarantee that a manual search cannot find the best architecture because, it depends on how many man hours you have. But you could, for example, I searched across different combinations of LSTMs. I found 4 or 5, which were all 5 layered and 40 neurons in each layer. It's something that you might want to try in the first few attempts, and we see that at least on test data, we are able to get a few more percentage points of accuracy. Okay, so in general, it's saying that, okay, within 3 hours, you can probably, if you have access to a leadership computing resource, you can probably do a little better than manual search. So now, probably something that you're more interested in, how does it do on the science, right? So for example, we used training data from 1981 to 1989, the end of 1989. To train our LSTM, so coefficients from that time were computed. The POD was also computed only on the snapshots of that data set. The data set is weekly average sea surface temperature, so it was not literally every day, but it was averaged every week. And the prediction was and the trained data set. We did our training and validation using these two using this time period. And for testing, we went from 1990 to 2018, so that's why it's longer. And you can see that as we actually deploy our framework, as we get closer to the present day, we start seeing some deviations. That's basically speaking about a little bit of the extrapolation that might be creeping into the system. Although we haven't really. This should be 2018, sorry, not 2010. We haven't really sort of dug into why this goes askew all that much. Another thing I'd like to sort of mention to you for people who are already doing a bit of geophysical modeling, we are actually taking in 8 weeks of data as an input, and we predict 8 weeks of data as an output. So it's like a sequence-to-sequence prediction, right? But we don't have feedback. So this is important. That's why the error stays quite nice and bounded as we go towards the present day. We assume that the past is always available from a satellite observation, and the past is like the last two months of data. If you were to actually start at 0 and want to make a prediction all the way to 1500, in the sense of how a PD might work or a climate-based model might work, then the LSTM will fail because these ML methods have no guarantees for error accumulation or being able to deal with error accumulations. And that's been sort of a thorn in our side for quite a few studies. For this particular, we've sort of sidestepped the issue for now. Okay, so and how does it work? So we took these POD sort of predicted coefficients and we reconstructed the sea surface temperature. Obviously, these are only pretty pictures for the eyeball norm. They look okay, but I will show you some more quantitative comparisons in the next slide. So over here, our comparisons are with two state-of-the-art models. So HICOM is a model that's run daily by the US Navy on a supercomputing resource. It requires about 800 core hours per day for forecast, so it's pretty expensive. And this is actually used right now for emulating the SST, the sea surface temperature. So it's currently in operation. The other model we compare to is a climate system model. So it's not a perfectly fair comparison. It runs for a much longer duration from 1920 to 2100. Very important data set. It has a lot of implications for policy processes, climate change field. And this is a very, very large simulation. It requires 17 million core hours on Yellowstone. That's a HPC at NCAR per member. So it's basically an ensemble forecast, right? It requires 30 forecasts. So 17 into 30 and many, many petabytes of data having to be stored. So just from a reduced order modeling perspective, or from a surrogate modeling perspective, we actually end up, being competitive in that sense, right? So we of course we don't provide a forecast from 1920 to 2100, but we are able to at least make a niche for ourselves in this particular case. So in terms of more quantitative comparisons, so what we've done over here is we looked at the Eastern Pacific, which is generally the region of interest for a lot of sea surface temperature observers. So the CSM is, like I said, the really long-term modeling approach. So that's biased in a bit. It's not surprising. HICOM is the state-of-the-art short-term forecast model, and the blue line over here is the predicted, right? So you can see the predictions are a little more smoother. That's because we only retain like the 5 POD coefficients, right? Just to focus on that, and the truth is the red. So in terms of like quantitative metrics, we are competitive. I don't want to go ahead and say that we are better because no, we are not. We have a lot of things stacked in our favor in this particular case. But if you look at the RMSEs for our testing period, which was data which was available for HICOM online between 2015 and 2018, the RMSE that we were getting across this period was consistently lower than that of CSM and HICOM. But what we envision our method to be is a complement to these PD-based methods. Because now in our method, you can easily make a perturbation to the initial condition and see how that propagates. So now you can come up with ensemble statistics much more easier than, like say running a PD-based model 10 times and then calculating statistics from that. We could run our model 1,000 times. So that's the kind of area we're targeting, right? Okay, so and this work is actually accepted at Supercomputing this November, and it's also on the archive if you want to get a sneak peek of what's going to be published there. Okay, so we are extending this work to much more difficult data sets. So I've been working with a lot of people to try and actually extend this framework to a much more difficult data set, which is the maximum temperature over North America. So this is pointwise maximum temperature. So I have a summer intern who's looked at this, and of course, Bethany Rao at EVS and Vishwas, our moderator. We've all been studying this. This data set is much, much more finer. So you have a 1 kilometer grid. So we had to switch to Horvath to actually do some of our model training, preliminary results are promising, but there's a long way to go. So you can see for this region that encompasses Chicago as well, we're able to predict the weekly averaged predictions quite nicely. There's some bias though at the inflection points. In the winter, it's always, this is the summer, but in the summers and winters, we always get pretty bad results. So still working on this. Okay, so in summary, DeepHyper makes it easy for you to search for off-nominal architectures, in a vast search space. So if you have any tasks that could benefit from this, keep that in the back of your mind. And also model order reduction methods can act as a pretty nice complement to these PD-based geophysical forecasting methods. So we could potentially see uses for this in ensemble statistics and analysis. Okay, all right. So I think I have about 10 minutes left before I'm supposed to stop, so I will not take any questions now. I'll just take questions at the end, right? So the third part of my talk is related to some framework development that we've been doing, right? So the first two were more methodological. So now what we want to do is we want to see if we can sort of provide a framework for users to actually deploy these fancy tools into their existing computational workflows, right? And so the first one I'll be talking about is some code that we've actually made public on the ALCF GitHub repo. It's catching some steam now, but this code, I'm sure a lot of you already know about this, but this is related to the in situ coupling of TensorFlow. TensorFlow has a C backend, and OpenFOAM, which is of course quite heavily used, not just at Argonne, but in the broader CFD community for a wide variety of applications. And so what this lets us do is it lets us deploy offline trained models. So you could train in Python, deploy it in C using the C backend. Or very recently, we also had the capability of training on the fly. So while you're running OpenFOAM, your data can be accessed by reference by TensorFlow, and then you can go ahead and start training a surrogate model, for example, right away before hitting disk. So that removes a pretty big I/O bottleneck that I'm sure once we start looking at Aurora and large machines that generate tons of data, that we'd be happy to bypass, right? So we deployed a proof of concept study where we used a TensorFlow trained surrogate model for the subgrid eddy viscosity in a RAN simulation, and we were seeing a pretty dramatic speed up when the surrogate was being used because we didn't have to solve an extra PDE. And this is the coefficient of friction for a backward-facing step problem, and we were able to recreate that quite nicely at about a seventh of the compute time by using a surrogate. Okay, all right. So as an addition, this repository comes with a very nice tutorial, and of course you all know me, so feel free to reach out to me if you need any help with this, right? Okay. Another thing that we're working on that is not really public right now is embedding Python in C++, right? Or extending C++ with Python, depending on your nomenclature. What we want to do with this particular work, and this is very, very exciting, is actually have a general purpose hook to a Python interpreter from within your C++ code. And again, you can access data through by reference within this framework. So you have a Python interpreter that sits between C++ and is able to load Python modules. Right, and we've done this with OpenFOAM as well. So now with this particular framework, you can go ahead and actually do a lot of crazy things from your C++ code. So for example, if you want to actually do a proper orthogonal decomposition, like I said, what you might be doing previously is you might be having your C++ code or your Fortran code dump snapshots to disk and then load it up with either MATLAB or Python, or even maybe some C++ code that you've probably painstakingly set up to do this POD or SVD, but now you can just type it in using Python, and we all love Python, don't we? Because it's so easy to write, and we can very easily sort of modify this and not have to recompile because Python is interpreted, right? And just to give you a tongue-in-cheek example of how crazy you can get with this, so I have a Twitter developer account. I expressly used that I requested that to come up with this slide. But basically, within OpenFOAM, I was able to embed a Twitter app, which could go ahead and take the current, say, for example, line plot of a particular quantity and actually just tweet it directly. Now, this is an example that's kind of meant to make you think. I've also done it for NEC-RS. But basically, you can think of rapid communication of your results for sure. That's one thing. But the second thing you can think of is now you can use this rich API ecosystem within Python to actually pull data from an experiment or from an observation as it's happening real time and hook it up with your simulation, right? So there's a lot of possibilities over here. So you could do analysis on the fly rather than wait for data sets to all be on the disk and do it after the fact. Okay, another framework that we've recently sort of done some work with this summer is with my summer student Suraj, where we scaled, or we are still scaling, but we deployed generic reinforcement learning framework on Theta. So this is reinforcement learning at scale. So you have each node being able to do its own environment evaluation. And the reason we did that is because reinforcement learning is basically a episode hungry framework, right? So it requires a lot of environment evaluations. But in our case, if our environment is a PD solve or a molecular dynamics solve, it's probably very costly, right? So in such cases, what we want to do is we want to distribute on a leadership class resource so that each node can go ahead and evaluate an environment, and that can be all of those can be used to update your agent, for example, if you're using like an actor-critic method, right? So we've deployed it for a couple of, again, preliminary tasks. So if you must be familiar with the Lorenz test case. So this dynamical system, depending on your choice of control parameters, gives rise to chaos, where you have the trajectory flitting between these two attractors. But for a certain range of this parameter rho, what you end up having is you end up having the trajectory just settling on one of these attractors. So it becomes kind of like it converges to a fixed point. So what we actually did was we trained a reinforcement learning agent to make perturbations to our control parameters so that it wouldn't stay stuck only on one attractor. Right, and you can see over here that the black line is what you would have if you didn't control the Lorenz system. So it would just go ahead and end up in this attractor on the left over here. But by making perturbations, we were able to keep the system chaotic, and by increasing the number of compute nodes, we were able to reach our reward in a lesser CPU time. So we're still scaling this. This is a simple problem, so we weren't able to go up to 256 or 512 compute nodes, but that's on the horizon. All right. Another task that we've sort of spent some time looking at is how to improve, for example, the convergence of steady-state system solves. So, for example, in OpenFOAM, you could use something like SimpleFOAM. SimpleFOAM is a steady-state solver that requires the user to a priori prescribe what the relaxation factor of the velocity and the pressure field is. So you choose these are like under relaxation factors. So if you keep them at 1, so the new result of your iterative process is used moving forward. If you keep this to less than 1, then some component of your previous time step is retained. So you have like a so it helps with your solution not blowing up, essentially. And what we did over here is we wanted our agent to observe this particular state. Again, the state construction is something that you have to decide, and then tweak these convergence parameters ideally dynamically. And the goal is obviously to ensure that the number of iterations for convergence is the lowest. And we do this for a variety of inlet boundary conditions and geometries to ensure that we can converge in the least amount of time. So you can see over here, as we train our agent, initially you have some choices of these alpha U and alpha P that take about 2,000 iterations for converging, but over time we basically end up saturating to basically a factor of 4 speed up, maybe. So that was pretty neat. Again, when we scaled it on multiple ranks, again, OpenFOAM itself is not very good for scaling. So we have to look for some more test cases that help us leverage the large resources on Theta, but we could see speed up by increasing the number of ranks. Okay. All right, so I will stop now. I have 5 minutes left, so I can take some questions, but before finishing, a colleague of mine from NASA Langley, David, and I are organizing a mini symposium in Chicago actually next year. There's a lot of time, so you can think about this quite deeply. It's the U.S. National Congress on Computational Mechanics. You can look at our abstract here, but basically we're soliciting talks for anything, adjacent to what I've talked about today. So reduced order modeling, closure modeling, anything that helps you avoid having to, pay a huge cost for these high fidelity PD solves. There's a lot of time. Abstract submissions open on the 15th of November, but if you're interested, I encourage you to submit something here since it's right next door. And of course, they have some student travel awards. So if you're collaborating with a student and want to bring them to Chicago, maybe this is a good opportunity as well. This is assuming that, things actually happen on site next year. So.